Yep, we've waited long enough. Okay, so we are now in chapter 11. Chapter 11, properties of solutions. So we'll start the math in this chapter. I don't think, well, yeah, I don't think any of the math is bad, but I've been doing this for 20 plus years. So we'll just try to ramp it up slowly. It really shouldn't be too difficult. Your written assignment from last week does have a couple of Clausius questions on it. So you're going to make sure you're able to calculate the pressures. There is a question on there about figuring out the molecular formula from the unit cell. It is a large unit cell, the perovskite. So again, when you look at it in the textbook, you're going to see the cubic sections, and then you're going to see like a diamond section off the top left. Ignore the atoms that are in the diamond section outside the main cubes. Okay, just count the atoms inside the cubic sections. Those diamonds are there to show you the difference in the structure. The one on the left will show you a full diamond structure, which is a proper perovskite. The one on the right, you'll see is lacking atoms to make the full structure. All righty. So, solution composition. So we want to be able to describe what's in a solution. Since solutions are mixtures of different things, we now want to be able to start talking about how much of compound A, how much of compound B, so on and so forth, are in the solutions. So one way we've been doing that so far is with molarity. So our concentration in terms of moles per liter. And it does kind of help to make sure you understand what order these are in. So it's like moles of solute per liter of solution. What is if you made salt water and you poured the salt into the water, which one is the solute? The salt. So just make sure we know these terms and which way they go. I thought it was, I felt that when I saw that. Now we have a couple of other ways that we're going to be talking about composition of a solution. So mass percent. So mass of the solute divided by mass of the solution times 100. So you can figure out how much of a certain solution is this compound, or this is something that's done quite a bit in geology. You want to figure out how much of a certain mineral, or I hate to use the word rock. It's just, but anyway, how much of it is, say, calcium? How much of it is? Now, a couple of years ago, we did have a geology student here named Zen. I wish everybody could have met Zen. Every time he did a presentation, he went to NAS with this, and he got up in front of all these professors to do his capstone. He goes, his opening, he goes, so I have this rock. Every presentation he did, that's how he started it. It was amazing. I also admired that guy because he basically crafted his own scientific degree, and he only took the classes he needed to be able to homestead in Alaska. And that's what he's doing now. He took the proper biology, chemistry, geology. He put it all together so that he could homestead efficiently. And that's what he's doing now. A couple months ago, I heard from him and he was excited. He goes, you're not going to believe it. I attached a shed to my house and I've doubled my square footage. Apparently, I didn't understand what homesteading meant. I was a little surprised. We also remember that we have this fun little thing we can calculate called mole fraction, that you see on the bottom. So again, Greek letter chi. So it's going to be the mole fraction of whatever compound A is. And that's going to be the moles of A divided by the total moles in the system. I'm going to continue getting used to higher order mathematical expressions. That big symbol there, what is it? The summation, what's the Greek letter? It's a Greek letter for S. Now I've seen people in movies and whatnot use that as like it's a funny E. It's not. It's not. That's an S. Yeah. What? Yeah, that's your capital sigma. So you have that. Remember, we were working with sigma bonds. That's lowercase. So that's the lowercase version of that. Now, kind of a new one here is the concept of molality. Molality is going to be moles of solute per kilogram of solvent. Do you notice how the denominator switched from solution to specifically the solvent? Make sure you're paying attention to that. You have moles per kilogram, but make sure you know kilograms of what compound. With this one, your units can either be moles per kilogram. You can also have a unit of just lowercase m. Here you have a nice little table of different kinds of solutions you can have and what their final phase is. So it's like, what? When carbon dioxide is dissolved in water, your solvent is a liquid, your solute's a gas. You end up with a liquid solution. So just how we mix different things. Laboratory technique. Does anyone know how we mix a gas into a liquid? It is. How do you do that? Well, yeah, that's one way. Another way that we do it, if we don't have a high pressure chamber, is you just put a tube in there and you bubble it in. Yeah, high pressure chamber will also do it. So let's say we have an aqueous solution of antifreeze. It's 40% ethylene glycol by mass. The density of the solution is 1.05 grams per cubic centimeter. Calculate the molality, molarity, and mole fraction of the ethylene glycol. Okay. So what did I use here? All right, let's start with the mole fraction. I started there because I thought it was easiest. I have to make an assumption that makes this easier. It's 40% by mass. And what are the two compounds in here? You know one of them has to be ethylene glycol. What's the other one? Water. Why? Why is it water? No, what phrase in that question tells you it's water? Aqueous solution. So when you're reading problems, make sure you're picking up everything that's there. Aqueous solution means dissolved in water. So, does anyone know an assumption that I could make? I'm hoping you did this last semester for problem solving. That's going to make this real simple for me. Tell me how many grams of ethylene glycol and how many grams of water I have. What could I assume that would turn 40% into 40 grams? 100 grams of solution. All righty. Now, mole fraction. So we have to have the moles of the ethylene glycol over the total moles. All right, well, we do moles of our ethylene glycol. What? We're going to say we have 40 grams of that. And then, how would I find the molar mass of C2H6O2? Yeah, add it all up. So what you're going to get, 2 carbons, 6 hydrogens, and 2 oxygens. You're going to get, over here. Now, how does that go into the equation there? Divide it, because I want to divide out the unit of grams. This is going to give me 0.644 moles of ethylene glycol. And then, of course, our moles of water. I'm hoping by now you're starting to have some of these molar masses memorized. Does anyone remember what water is? 18.02. So give me 3.33 moles of water. All right, so our mole fraction then. Okay, so we're going to have 0. I don't need the parentheses, but my mole fraction will be 0.162. And you do know that you can you can think of mole fractions as percentages as well. So this solution would be about 16.2% ethylene glycol. Okay, so we have our mole fraction. Let's do molality next. And again, this is just the order I did them in. If you're solving problems like this, you can do whichever one, you can do them in any order you want. Now, we remind ourselves that molality, moles per kilogram. Now, how would I go about this? Moles of solute per kilogram of solvent. This is why I started with mole fraction, or at least my assumption. Do I know my moles of my solute? Do I have a mass of my solvent? What is that mass? It is. Let's just start with the 60 grams and then go from there. So my molality, I'm going to start with my 0.644 moles of ethylene glycol. /60 grams of my solvent, and then I can say of 1,000 grams in a kilogram, that's going to give me 10.7 moles per kilogram. And last, we are going to do molarity. And molarity, moles per liter. Okay, well, again, I know the moles of my ethylene glycol, and that liter, the liters there on the bottom. So the last one was kilograms of solvent. This is liters of what? Whole solution. Now I don't have liters of solution. I have an assumed grams of solution. Now I will tell you another conversion that I used is that one. You could also use 1 liter as 1,000 cubic centimeters if you wanted to. Just depends on which one you remember. No, darn it. Supposed to be the 400 grams. So remember, we assumed 100 grams of solution. Now, how do I start getting this from grams to cubic centimeters to liters? I have 100 grams of solution. Let's go back up and look at what we have in the problem. Use what? Yeah, I use the density. So that is going to be 1.05 grams per cubic centimeter. 1 cubic centimeter per 1 milliliter. And then, of course, there's 1,000 milliliters in a liter. And this will give me 6.76 moles per liter. So problems like these, you just got to think about what you have. Start with what you have and start putting in different conversions until you end up where you need to be unit-wise. If you're ever on an exam where you have to watch your time, one of the ways you can solve problems is like if you need to know the density of something. Well, just remember, like you say, well, I know density is mass over volume. What numbers do I have here, and how can I put them together to get mass over volume? You can actually start to solve you can solve problems by looking at the unit you're supposed to end with. Okay, this one you need to know it exists. I'm not really going to give you homework problems or test questions over this. Another way to explain a solution is by normality. So it's the number of equivalents per liter of solution. Okay, so normalities are going to be different based off the different types of solutions you have. It's different for redox equations. Some of the equivalents have to do with electron transfer. Acids and bases are pretty straightforward because it's an equivalent is the mass of the acid or base that converts exactly 1 mole of proton. Okay, so here we have H2SO4. What is it? What's the acid group? Sulfuric acid. So if I look at that, I have 2 protons on there. So that's called a diprotic acid. And so the sulfuric acid is going to give off 2 total moles of protons. The ammonia is going to accept 1 proton at a time. And if we have 2 moles of ammonia, you'll end up getting both moles of protons accepted. So your number of equivalents is going to be 2. The diprotic acid gives off 2 total moles of the protons. Now, the equivalent weight that you're looking for, your sulfuric acid is 98.1 grams per mole. You're going to take that molar mass, divide it by the number of equivalents, and then your equivalent weight is 49.05 grams per mole. That is the mass of the sulfuric acid that will give off exactly 1 mole of proton. Yeah. So it's a small section of the chapter. I want you to kind of have an idea of how it works. You may see it at some point in the future, but just know that this is another way we can describe a solution. Alrighty. Uh-oh. Let's see if you can answer these. What do we think for number one? It's what it's yeah, it's molarity because that's moles per liter. So let's think about the others. Uh, molality, moles per kilogram. So no matter what I do to the temperature, will the number of moles in there change? No. Will the mass in there change? So what changes in molarity that temperature affects? So that and that'll change what? So you said it, the volume. So volume can shift based off temperature. Yeah, evaporate, expand. I think a good way to think, no matter what phase the solution is, think of PV equals nRT. We know that volume and temperature are directly related. What about number two? We just talked about normality. Can you make like if you got a standardized exam where you're like, oh, I have to make a guess here. Look at that compound. What do you think is going to dictate the equivalence on there? This is going to form a basic solution. And a basic solution, the compound you put in the solution gives off what? Hydroxide. So what do you think the answer to that one is? B. This is going to be dictated by giving off hydroxides into the solution. Okay, so when you're making solutions, I would take this first rule here and sear it into your brain. Because you're going to need to bring this back up when you get to organic, when you get to biochem, and it's the idea of like dissolves like. You ever seen oil poured into water? What happens? They separate. So is water a polar or non-polar solvent? It's a polar solvent. Oils filled with lipids, are those polar or non-polar? Non-polar. So you have a non-polar solute mixing with a polar solvent and you see what they do. Now, what would happen if you poured the same oil into benzene? Is benzene a polar or non-polar solvent? It's non-polar. So benzene will actually dissolve the oil and separate it out. But then you throw salt into water. Now, salt isn't what we call polar, it's what? It's ionic. So polar solvents are also going to dissolve your ionic compounds. Basically, you're looking, is there an overall charge? And so like my polar solvents will take apart ionics and polar solutes. And so then we're going to want to mix nonpolars with nonpolars. Now, when we're talking about energies of solution formation, we have to look at this in several steps. So we separate the solute into its individual components, we expand it. Like again, let's say it's sodium chloride. That's going to be breaking apart the sodium and chloride ions and spacing them out. And then you have your let's say water, your solvent. You're going to have to space that apart. So in water, we'd be breaking down the intermolecular forces, the hydrogen bonds, to pull the molecules apart to make room for the sodium and the chloride. And then we allow the solute and solvent to interact to form the solution. All of these are going to have associated energies. Okay. Did I put that out of order? No. Okay, so you kind of see that process here. So you see you have a solvent, a solute crystal. You're going to have enthalpies involved with pulling each of those molecules apart, and then they're going to mix, and you're going to have a third enthalpy, which is going to it's usually going to be exothermic upon the mixing, because you take, for example, water and your salt crystal, the ions in the water are going to start to form dipole ion like interactions, and it's going to decrease the energy of the system and let heat out. And so what you have here is the total enthalpy of your solution will just be the sum of all of these different process enthalpies. So there you see sodium, and one thing to pay attention to is these processes are usually done by first splitting your solute apart in the gas phase. So you can get energies for that. So there you see sodium chloride split into sodium and chloride ions in the gas phase. That is going to take 786 kilojoules per mole to do that. That's a positive enthalpy, which means what? So a positive enthalpy. It's taking in energy. Do you remember what we call that? Endothermic. So then, of course, the water molecules are going to have to be expanded, and then that's going to be breaking down those hydrogen bonds, and then your water is going to mix with your sodium and chloride in the gas phase, and you're going to get aqueous sodium and chloride, which will give you your delta H3. Now, sometimes the 2 and the 3 are left out, and it's just called an overall enthalpy of hydration. So the enthalpy of hydration is really, you take your solute, split it apart, and then you just dump everything into the water, and the water is going to split, and then everything's going to mix. That's the hydration. So your overall enthalpy of hydration is a negative 783 kilojoules per mole. Now, for this whole process, I add those together, and you see I get a total of 3 kilojoules per mole, which means that the actual mixing of salt into water is going to be an endothermic process. So some of these processes, when you do the total enthalpy, you'll get a negative enthalpy, which is exothermic. Sometimes it's a positive enthalpy, which is endothermic, meaning energy has to be put in to accomplish this. So here's another way you can look at it. Well, order has to do with entropy. Enthalpy is really just the heat of a reaction. Now, the sodium chloride, you're going to see a nice little term here. So that's 786. I've said this term before. So it's the energy of this crystal that's governed by Coulombic forces. This is the energy you're going to need to break down those Coulombic forces and split the ions apart. Do you remember what that's called? It's the lattice energy. Let's look at a problem here. So we have some data, calcium chloride and calcium iodide. The lattice energy of calcium chloride is negative 2247 kilojoules per mole. Calcium iodide is a negative 2059 kilojoules per mole. And so this is a good question. Why is the lattice energy for calcium chloride stronger than the lattice energy? So remember, negative energies, the more negative the energy, the more stable the compound. So why is calcium chloride more stable? Why is the lattice energy greater than the lattice energy for calcium iodide? because we're dealing with combinations of a +2 calcium and -1 chloride or iodide. So the two charges are the same. Why is one stronger than the other? Not electronegativity. What if you remember Coulomb's law? The electrostatic force going to be Coulomb's constant. Well, Q1 and Q2 don't change. Those are your charges. What is that R? It's what? So yeah, you're getting there. Do you remember what the R is? Well, more general, it's the separation between the two ions. So it's the distance of separation between the charges. And so what's governing this is ionic radius. So your calcium radius is going to be the same for both of them, but the iodide radius is larger than the chloride radius. So the R is greater, which is going to decrease the lattice energy. Space the charges further apart, you get a lower energy, a lower force of attraction. Okay, so let's see if we can figure this out. Okay, so we have our delta H of solution. Now, I told you we can skip like delta H2 and 3 and just call it delta H of hydration. So let's kind of put this together in terms of Hess's law. Does anyone remember that term from last semester? Okay, so Hess's law is really, if we have a step-by-step process and we have enthalpies of those processes, we could just add them all together. That's Hess's law. So what we're going to do is, the first thing we're going to do is we're going to take the calcium chloride and split it up. Yep, it's two of those. Okay, the delta H for this, well, enthalpy 1. Now, you see that lattice energy of negative 2247 kilojoules per mole. We are splitting this compound apart. It's going to take that amount of energy to split it apart. Do I use a positive or negative number? If it's stable by negative 2247 kilojoules per mole, what do I have to put into that to break those apart? Positive 22. So it's going to be you can either call it the negative of the lattice energy, or so that's going to be a positive 2247. We're just going to call it kilojoules because we're imagining everything is 1 mole here. So it's going to take at least that amount of energy to start to break this crystal apart. Then we're just going to go to the hydration stage, where your calcium and your chlorides are going to go from gas to aqueous phase. That's our enthalpy of hydration, and we don't actually know that. We're trying to figure that out. So then Hess's laws, I'm going to add all these, I'm going to just add everything together. And so you notice that my gas phase ions are the same on both sides. So when I add this, and then we're told that the delta H of our solution is going to be negative 46 kilojoules. So we have to figure out what the enthalpy of hydration was. Okay, well, by Hess's law, we could say the enthalpy of solution is going to be the first enthalpy plus our enthalpy of hydration So the solution enthalpy minus the first enthalpy. And so that'll give us well, we are going to have the solution enthalpy is a negative 46 kilojoules minus 2247 kilojoules. Our enthalpy of hydration is going to be a negative 2293 kilojoules. So now we have to do the same thing for calcium iodide. So why do I call this calcium iodide, not calcium 2 iodide or calcium diiodide? It's ionic, so I don't use the di prefix. What about, why don't I call it calcium 2? Well, yeah, it's not a variable charge ion. So calcium is a common charge ion. Let's see. So we just need the negative of our lattice energy, which is 2059. All right, now we're going to do the hydration phase. So that's our enthalpy of hydration. Now we're going to add everything by Hess's law. And so our delta H of solution will be negative 104 kilojoules. And once again, we can solve for the enthalpy of hydration. Hope you remember from above, this is going to be your solution enthalpy minus your first enthalpy. So now we have the hydration enthalpies for each one of these. So let's see if we can answer part B. Which ion, chloride or iodide, is more strongly attracted to water? Look at those two hydration enthalpies. Which one would you think? Now, when we put these into water, why doesn't the calcium play any role in this answer? So it's only the negative ions that are causing the difference here. Why am I not considering calcium? Is what? Nope. Because calcium is common to both of them. Calcium can't be what's causing the difference. So based off these numbers, which one is more strongly attracted to water, the iodide or the chloride? Chloride. Why? It goes lower than the other one. So again, we remember negative energies means stabilization. The chloride stabilizes more in the water than the iodide does, meaning it interacts more strongly with the water. Did anyone in here enjoy thermodynamics the first time around? No? Man, nobody's ever going to take my chemistry 400 level course, statistical thermodynamics. A lot of fun. Okay. Factors affecting solubility. This is why I confused myself. For some reason, I wrote this before I solved this problem. Okay. So structure effects. We kind of talked about this before. Here's two fun structures for you. Vitamin E and thiamine. What is thiamine? What vitamin is that? B12 has a porphyrin ring with a metal in the center of it. Usually cobalt. You're getting closer. Thiamine is necessary for healthy neural responses and nervous responses. What are the B vitamins? Getting closer. B1. B1. That's vitamin B1. And of course, he has vitamin E. Now, fat soluble versus water soluble vitamins. What's the difference in the solubility? Polar, not polar. Fat soluble are going to be what kind of molecules? Non-polar. Water soluble, of course, will be polar. Water is a polar solvent. Fat, more lipids. So that's going to be a non-polar solvent. So which one of these do you think? Well, it kind of tells you up there, but why do you think vitamin E is fat soluble? I mean, do you see the hydroxide over there? Wouldn't that be a polar region? What about that oxygen on the ring? Wouldn't that be a polar region? Why is this soluble in a non-polar solvent? You see the extremely long hydrocarbon chain? So it doesn't matter that if there's a hydroxide over there on the ring or that there's an oxygen in another ring. This hydrocarbon chain is so long that it's overpowering any polarity this molecule has. And this is a non-polar molecule. So again, remember, the longer the hydrocarbon chain, the more non-polar it becomes. And really, your limit's going to be right around that 3 to 4 carbon. Anything like 5 carbons and beyond, you can really designate them as non-polar. The thiamine, water soluble. And what kind of polarity do you see in there? Oh yeah, you're going to have that hydroxide. Yeah, you see the amine group on there. The nitrogen in the ring is going to have lone pairs. That one nitrogen is already positively charged. There's polarity all over this molecule. And you don't have a long hydrocarbon chain to cancel it out. So these are structure effects that affect solubility. Pressure effects. This is one of the harder equations we'll work with. So gas solubility can be increased with pressure. I think you already brought that up. So again, we can put a gas in a chamber with a liquid. We can put a lot of pressure in there and force that gas into the solution. And we really examined this through what's called Henry's law. Henry's law, C equals Kp, C is the concentration of the dissolved gas, K is a constant characteristic to the solution, and P is the partial pressure of the gas above the solution. For me, it's usually both. All right, let's work a problem with Henry's law. Actually, you guys take a few minutes to see, because this one is very straightforward. I want to see if you can solve it. Let's see. K is your Henry's law constant. Now pay attention to the constant and the pressure you're given. What do you have to do to those? Yep, you have to make a match. So the torr has to become atmosphere. No, the temperature is not going to play into this one. And when it asks for the solubility, so sometimes this can be a little confusing the way questions are asked. When a problem asks for the solubility, it wants to know what is the concentration of the gas in solution. So C stands for solubility. Yeah, it's concentration or solubility. That's all it's asking in this case. What concentration of the gas do you have in solution at this pressure? Mhm. Did people get around 2.05 times 10 to the negative fourth? So some of these are going to be very straightforward. This is kind of a nice little break after doing those reaction enthalpies, but so what you have, when it asks for the solubility, it's saying, again, it's saying, what is the concentration of gas in the solution at this pressure? So we see our constant is in terms of atmosphere, so we have to change the torr. And what, that's 760 torr per atmosphere. The pressure is going to be 0.158 atmospheres. So the concentration in solution is going to be 1.3 to the negative third moles liter atmospheres times 0.158 atmospheres. The concentration or the solubility will be 2.05 times 10 to the negative fourth moles per liter. Okay, so got lucky. We'll start with vapor pressure next time. Raoult's law, French name.